All right, I think it's time to start our webinar. So, hello, I'm Nicolas Vogt from HQS Quantum Simulations, and I want to warmly welcome you all to our webinar today. If you have any questions, please use the Q&A function of Zoom, and I'll get to you later once we are finished with the presentations. The topic for today is a quantum simulation use case for electron spectroscopy. Electron spectroscopy is a whole set of experimental techniques that have in common that in the experiment, an electron molecule gets excited and is emitted from the molecule, and then the energy is measured. And one of the things that one can do with this experimental technique is to determine the energy splitting between singlet and triplet states of a radical. And that has potential applications, for example, in photovoltaics, in luminescent devices, and in other technical applications. And what we now want to do is we want to use the quantum computer to make an ab initio prediction of this singlet triplet splitting, of this energy gap that can be observed in experiments so that we can compare our ab initio prediction with the experimental technique. And since this is a technically very involved process, in this webinar, we'll be focusing on the quantum simulation aspect of it and the technical details, and not so much on the application. And if you want to know more about the application side, I can recommend that you look up HQS on the archive and check out our recent white paper on use cases for the quantum computer. So, what we want to do is we want to predict the singlet triplet gap in the radicals. And what one traditionally needs to do for that is one has to choose a basis set for the molecule in question, and then each of these orbitals in this basis set can be occupied or unoccupied by an electron. And of course, the energetically very low-lying orbitals will all be completely occupied, and the very high-lying orbitals will be completely unoccupied. And one needs to define or find the so-called active space, so the space in the middle where there's a mixture of occupied and unoccupied orbitals. And this in itself is already a highly non-trivial task. And once one has defined this active space, one, of course, needs to find the correct states for the singlet and triplet states, the correct eigenstates of the problem to determine the energies. And if you now want to do that on a quantum computer, that is, of course, in principle possible. However, it is a very hard problem because encoding fermionic degrees of freedom that we're dealing with here on a quantum computer leads to a large overhead. For example, if we use the Jordan-Wigner encoding, and also chemistry is messy. So we have so-called 4 index terms here, so 4 different orbitals all coupling together, which is a huge overhead and not in the near term feasible on a quantum computer. So what can we do? And the answer is to apply a transformation that is inspired by the so-called random phase approximation, RPA, that can transform the problem to essentially a spin boson problem. And spin boson problems are well known, they're well studied, and we know how to bring them onto the quantum computer. So essentially in this transformation, what happens is large parts of the majority of effects of the active space are encoded in an bosonic environment. So bosonic is important here. And only a 4-level system remains that encodes this singlet triplet physics. And the rest is done with the interaction with the bosonic baths. And I'm just giving the motivation here. So later on, what you will see in the course of this webinar are 2 things. So the first thing is when we do this transformation and we arrive at our effective model, we need to check with classical computations that our transformation gives reasonable results. So we need to do a cross-check. And to do this cross-check, we need to do the calculation with lots of qubits. And we can use some tricks to make this feasible even on classical computers, although simulating large systems on classical computers is hard. And what we can use for that is our quantum solver. And my colleague Hannah will give you an introduction to it and show you how we can use our quantum solver to use the fact that we only have few excitations in this mapped system to get a comparison solution. And then in the second part of this webinar, my colleague Dima will show you how this RPA-inspired transformation actually works and what results we get from it. Sorry. All right. With that, I would hand over to Hannah.
All right. So, yeah, as Nico said, we'll be focusing on the classical simulation now. And yeah, so when running complete space simulations, it's important to pick the right subspace for your quantum state, because it makes the difference between feasible computation and completely impractical computational resource requirements. So in this presentation, I'll show you how to use HQS Quantum Solver to tailor quantum state spaces to make a simulation with a large number of spins possible on conventional hardware. Okay, so first of all, I'll give you a very quick overview of what HQS Quantum Solver is. HQS Quantum Solver is a Python library / toolbox that provides methods for simulating quantum mechanical systems. What it does or implements is a complete space approach, which means that there's no mean field or something similar going on. You define the states of your quantum system or all the states that the system can be in, and across those states, the computation will be exact. And then it has ways to construct quantum mechanical operators for spins, fermions, and bosons, and their computational methods like the time evolution or solver of the Lindblad equation, and other stuff that you can use to actually do more with those quantum mechanical operators. So, since quantum mechanical systems are described by linear operators, and linear operators are defined on vector spaces, there are ways in Quantum Solver to define vector spaces, and the first step into the direction of doing anything meaningful would be to look into how to use vector space definitions in HQS Quantum Solver. So there is, and during this talk, we'll be focusing on spin systems alone. If you want to learn more about how to use this, the software for fermions or bosons, things are pretty similar, but you find good examples in the documentation. So a vector space is defined by a vector space class in Python, or that's in a Python class. And as you probably know, in quantum mechanics, we define the vector space by the quantum states that the vector space represents. Each state that the system can be in gets a dimension in the vector space, or is assigned a dimension in the vector space. And that means that we're defining essentially the vector spaces in Quantum Solver by defining the states of the system. By particular choices of states, you can actually enforce certain conservation of quantum numbers. You have to be a bit careful about that. You should know what you're doing. In most cases, you should be getting an error if you're doing something unreasonable, and this becomes relevant later. Obviously, the space should be as small as possible to get the most performance. And here, as an example, so what we're doing is we're creating a vector space object, and we're providing here the number of particles, which is the size attribute, and we specify the total spin z value, which means that the sum over all spins in the system in this case is 0. So with that, let's look into a bit of code here. So I have already prepared the necessary import, so we can essentially take the code from the previous slide and see what happens. So I create this vector space, and if we look at the output, that just means that so far we have just looked at the parameters that we've defined, but we can also look at the states that are represented by the vector space. And what we see here is we have set, we wanted to have 4 particles, and the total spin z should be 0, which means we want to have as many up as down spins. Okay, so the next thing, obviously, what we can do is we switch to maybe a total spin z value of 2. Note that the total spin z value here is measured in units of 1/2. So if you're thinking of spin 1/2 particles, that means if we specify a value of 2, that now means that we have now 3 spins in the up state and 1 in the down state. Or if you want to say, that means we have, if you're thinking of particles of spin 1/2, we're having a total spin of 1. But so far as this attribute goes, you can think of basically the difference in number of up and down spins, which makes it maybe easier to think about this. So another thing, you don't have to specify the total spin z value completely. This doesn't have to be a fixed number. Another thing that we can do is we can start with a particular number of total spin z, and then say that we want all multiples of, or we allow for changing the value of the total spin z in certain steps. In this case, if I write, if I give a tuple 0, 2, that means we're starting with a total spin 0, and then we allow all other states that differ by a multiple of 2, which in this case means that we're essentially getting all the states. For example, if we now put in here a value of 4, we see that we also get the state, all the states where the number of up spins and down spins are equal. But also, if we remove 2 spins in the up state and put them in the down state, we get the state where all the particles are in the down state. And if we remove 2 particles in the down state and put them in the up state, we get the state where all the particles are in the up state. And there's a shortcut for the state where basically we just have no restriction on the total spin z value, so you can just type all here to get basically all the possible spin states. There's another way of defining, or let's say, tailoring vector spaces, and that's combining of different vector spaces. So let me create a vector space with 3 particles and total spin z equal to -3, which means basically this will be just all the down spins. Okay. And I'll create another one, v2, where I just set total spin z to 3, which means that we're getting just all spins are in the up state, and we can combine the two spaces, or that we can take the union of the states that the 2 spaces are representing by using the pipe operator. And then if we look at this, we actually get the space that represents both states. Okay, another way of combining vector spaces is to use the tensor product. And let me copy this here. Let me take the space where v1 has a total spin z of -1 and v2 has a total spin of 1, which means that we're getting all the states, whereas 1 spin in the up state and the other in the down state, and in v2 it's the other way around, so 2 spins in the up state and 2 spins in the down state. What we can do is actually compute the tensor product of the 2, which means that we're getting all possible combination of the two states. And in the first indices, we obviously get all the states of V1, and the second half, all the states of V2. So you can see that in the first half, we get all ways of having a particle, one particle in the upstate and two in the downstate. In the second half, two in the upstate and one in the downstate. And we get all possible combinations of those. So with that, no. Second. With that, we have now a vector space, and we can actually construct operators, so quantum mechanical operators. To create an operator in Quantum Solver, you need to specify the domain, and furthermore, the codomain of those differ. In our case, it won't. And we provide a term that describes the operator. Operator terms are linear combinations of terms, which are lists of functions that we are provided in the spins module. And you see what that means in details in a few seconds. If you have constructed the operator, it will provide you with matrix, and matrix vector or operator apply to a vector or operator to apply to a matrix methods. And furthermore, the quantum solver operators are compatible with SciPy, so you can use the IKE-S function, for example, directly with the quantum solver. I need to take a sip. Sorry. Okay. So in this example, where you see we just created, as seen earlier, we create a vector space, and we provide the term that defines the spin z observable for site 0, and we pass in as the domain the vector space V that we've created earlier, and we're getting the corresponding operator. So with that, we can actually look at a practical example now, and that will be building low-excitation subspaces, which will make a particular simulation that involves a large number of spins possible by using a clever choice of the vector space. And that allows us for running with large number of spin degrees of freedom on actually conventional hardware. So the system that we're going to look at will be the following. We're looking at the Heisenberg spin chain in the antiferromagnetic setting, which means that spins in neighboring spins on the chain kind of want to point in opposite direction. Then we add a magnetic field whose strength is less than the coupling strength, or weaker than the coupling strength between the particles in the Heisenberg chain. And finally, we add a bunch of surrounding spins that weakly couple to all other spins, which means that the magnetic field will actually dominate the surrounding spins, since the coupling of the surrounding spins is not that big. And for that, we will only expect a slight excitation in the surrounding spins, which means that we can actually reduce the computational effort, as I'll show you in the next slide. So we need to write down the mathematical formulation of the system, which which looks like this. We order the degrees of freedom in the Heisenberg chain in the first n1 degrees of freedom, and the surrounding spins, n2 surrounding spins, are numbered after that. And then the Hamiltonian of the system looks like this. So we have the magnetic field term in the front, and then there is the strong coupling of the Heisenberg chain. So we have for neighboring spins, we sum over the scalar product of the two vector spin operators multiplied by the strength of the field of the interactions of the interaction. And finally, the last part is the weak interaction of all the spins, or weak interaction between all the spins, which we take a random matrix for pairs of spins here. that has, well, a certain size. So since J strong and J weak will be positive, we're in the antiferromagnetic case, because minimizing the energy means actually having the spins pointing in opposite directions. Okay, so now the clever thing now to do is to actually construct the space that we're doing the simulation on by taking the tensor product of two spaces. The first one is the represents all the states that the Heisenberg chain can be in, and the second space defines the states of the surrounding spins. And there, because we only expect a slight excitation, we limit it to all the states where at most one spin is in the up state. So, with that, we can actually jump into implementing the entire simulation. I've prepared a bit, so we're doing the necessary imports, and we're defining the parameters of the simulation. So we have the sites in the Heisenberg chain stored as saved as sites part 1. Sites part 2 is the number of states of the surrounding spins. We set B as the field strength to a negative value to make it point in the downward direction, and we set J strong to 1 and J weak to 0.2. So with that, we can now start building the vector spaces as we've seen before. So this is no surprise. It's essentially what we have seen earlier. So we're setting the sites to site part 1. And since we want just all states for the Heisenberg chain, we just provide all and get the corresponding vector space. For at most one spin in the up state, we have to combine two spaces. So let's first take the space. Obviously, we're dealing with the surrounding spin, so that's sites part 2. And now the total spin z. If I set the total spin z to actually negative sites part 2, that means, if we're looking at this, that we're getting the states where just all the spins are in the down state, because basically the number of, that's how the definition of this works. And we can combine this by taking one spin in the down state and putting it in the up state, which means increasing the total spin z value by 2. Right? So this plus 2, since we're measuring in units of 1/2. And if we're doing that, we're getting all the space, all the states where at least, at most, one spin is in the up state. So we have built this vector space, and the final thing is just to take the vector space and build the tensor product of the two spaces. So now that we have the vector space, we can actually go continue with building the Hamiltonian. For that, we'll be using two-term functions that provide terms, operator terms, the magnetic field Z function and the isotropic interaction function. So, okay, let's take a short look at the documentation. What you can see here, that the magnetic field Z term is already almost what we want. What it does is it expects a vector as an argument for the field strength at each side in the Z direction. So the thing that we have to do to actually get constant field strength across all spins is to just create a constant vector with the appropriate value. So if I write this, I just use the standard NumPy, function MP full to create the constant vector. You see that this is actually what we want. And I define the field term as the magnetic field Z function, and I provide exactly this vector. Okay, so this is the field term. The next thing is the strong interaction term. And there's the isotropic interaction function, which basically gives you the spin-spin interaction by providing a matrix where the matrix element jk describes the strength of the coupling between the particle at site J and the particle at site K. So for the Heisenberg chain, that means we want to have the links. So we want to have the J plus 1 elements set to J strong, which means that we're getting, for each link, we're getting 1 here in this first upper diagonal part of the matrix. So we can very straightforwardly do that. So what I essentially do is, and I won't go too much into detail here, I just say I want for the indices that are smaller than the number of sides -1. So smaller than the number of links, the number of links will be in the will be the number of ones that we have. We set this to 1 and otherwise to 0. So that's that. And then we can define this the term describing the strong interaction by calling the isotropic interaction function and multiplying as the coefficient vector, multiplying the strength of the interaction and putting the vector that you see here below into the first upper diagonal. So this, what have we done? Oh, I need to call the Dirac function. Okay. So this gives us the strong interaction, and the weak interaction is just a random, a strictly upper triangular random matrix, because otherwise, if we just take a full matrix, we have the terms come up twice because Sj times Sk is the same thing. So we just take the strictly upper triangular part of this, and I'm gonna grab a random number generator to get a random matrix, and so the coefficient matrix for the weak interaction is obviously we need to multiply the whole thing by the strength of the interaction, and then we just generate a random matrix and take the strictly upper triangular part. Which means, so I want a uniformly distributed matrix of side V sides times V sides. And from this random matrix, I just take the strictly upper triangular part. And so that means we're getting the weak term as the isotropic interaction function of this J weak matrix. And once we have that, we can actually just create the operator by just passing the field term plus the strong term plus the weak term. And that's where you see that we can just specify arbitrary linear combination of the terms, and we provide the domain as the vector space that we have defined before. Now note that the term that we have defined actually maps outside of the space that we have defined, which is oftentimes an error. But this time we are certain that this is fine, because we know that there won't be we know that the excitation in the surrounding spins won't be too large. So I will be passing strict equals false as an argument so that we are not getting an error. So with that, we can actually compute the energy levels of the system by computing the eigenvalues of the operator. So I compute the eigenvalues and the eigenvectors just by using a standard SciPy function. As I said earlier, we can just pass in the quantum solver operator to the SciPy solver, and we want the smallest algebraic eigenvalues. do the computation. Takes a few seconds. So, and with that, we can actually plot them. So the energy levels look like this. Finally, another interesting thing to look at is the ground state polarization of the system. So what we can do is just compute the expectation value of the spin z observable for each side. And I've already prepared the code here for time reasons. So what this does here is computes the list of observables that we want to have. We want to have the spin z at side j for all sides in the range of 0 to v sides -1. For each of those, we construct the operator, and then we essentially just implement this function. So we take the scalar product of a wave function times applying the observable to the same wave function for all observables. And then if we take the ground state and call this function for the ground state, we actually see that this, that this will be the result. So you see here the antiferromagnetic coupling between the spins in the Heisenberg chain with the first part and almost no excitation in the last part. I can now go to the top and actually increase the number of spins. So if you're doing quantum simulations, we're now at 42 spins, which is actually quite a large number regarding spin simulations. And this is my laptop, which is doing, which is running Zoom in the background. So this will also just take a while. And the thing, so the trick here is, and I didn't say this earlier, that actually the vector space for the surrounding spins only grows linearly with increasing number of spins. So that makes increasing the number of spins of the surrounding spins rather cheap. So what you can see here, again, we get the energy levels, and actually we also get a bit more excitations in the surrounding spins. Note that we had just a random coupling between those spins, so there will be a difference in those spin states here. Okay, and also I could, just for time reasons I won't, but running this with all 62 spins will run through in almost 2 minutes. So this is still something that you can do on a laptop very easily. Okay, with that, where to go from here? If you want to try it out yourself, you can go to cloud.quantumsimulations.de, make an account, request a free trial, so you can use Quantum Solver for a year if you want to. On docs.cloud.quantumsimulations.de, you find the documentation with a bunch of introductory examples. And if you go to GitHub in the HQS Quantum Simulations organization, in the HQ stage examples repository, you will actually find the code that I showed in this talk with comments and all the details that you might want to look at. And with that, I conclude this part of the presentation.
All right. Thank you very much, Hannah, for showing this to us and showing how one can use the quantum solver to exploit the properties of low excitation subspaces to make them actually solvable on classical computers. With that, I'll hand over to Dima to show the actual RPA-inspired mapping and also how we can use what Hannah just presented to solve it on classical computers for now until we get bigger and less error-prone quantum computers.
Okay. Hello, everyone. So I'm going to present the system bus model for quantum chemistry, which Nico has introduced briefly at the beginning and which we have recently developed in our company. So the basic idea, I just repeat briefly, is if we solve a molecule with non-interacting electrons, then it is easy to solve. Basically, we have a set of energy level, every level can be populated by 2 electrons with opposite spin, and the wave function of this whole system is in Hartree-Fock approximation. It is single-letter determinant. However, if we include interaction, it is very hard to solve this problem. Quantum chemistry is known to be a complicated field. What we are saying is that if we are interested in low-line excitation energies of the molecule, we can split it into two-part system and bus, where system is two orbitals with 2 electrons occupying them. This part can be solved exactly, and the rest we represent as a set of oscillators with coupling constant G1, G2, G3 coupled to the system, and these constants are actually very numerous, many thousands of them, but still one can solve many things. So why do we do this? Because the system bus models are very well known in condensed matter physics. People know how to solve them, use them all the time to describe, for example, qubits in quantum computers. And we want just to translate quantum chemistry to the language which we understand. Another thing is, of course, quantum computing itself, because as also Nico mentioned, if you want to encode a Hamiltonian of a molecule on a quantum computer, it is a hard task, because you need to represent Fermi creation-aggregation operators of electrons by long strings of Pauli operators. And in our model, the longest string of Pauli operators is only 3, so it is relatively simple to code. So what is the starting point of the modeling? It is a Hartree-Fock simulation of a molecule. So we take a molecule, run PyCF simulation. PyCF is an open source Python package, which is well known for quantum chemists. Out of that simulation, we get 2 arrays of numbers, T and H. T is basically a matrix element of non-interacting part of the Hamiltonian between the Hartree-Fock wave functions of a molecule. And then H is a set of Coulomb repulsion integrals, which are matrix elements of Coulomb potential, basically. And this number of these H integrals or Coulomb repulsion integrals can be huge. So if you take, if you want to achieve good accuracy for a molecule with, let's say, 10 atoms, we need to take 100 to 300 orbitals, and then this will be 300 to the power 4, which is a huge number, tens of thousands. So this is why quantum chemistry is difficult. Now, what is a system bus model? A bit more details about that. So if we take the original Hartree-Fock simulation, we have a set of energy levels with energies shown by horizontal lines. Every orbital below the Fermi level, this red line, is doubly occupied by a pair of electrons. And we just select the orbital just below the Fermi level and just above the Fermi level. These are so-called HOMO-LUMO orbitals. HOMO is highest occupied molecular orbital, LUMO is lowest unoccupied molecular orbital. And these two orbitals, together with 2 electrons populating them, is our system. And what is the environment? Environment consists of transitions between doubly occupied orbitals and empty orbitals. So one can basically create electron-hole pair or excite an electron from deep below the Fermi level to high above the Fermi level, for example. This arrow shows the transition at the same time an oscillator in the environment. There are also other transitions between the HOMO-LUMO orbitals and the environment. They should also be included to increase the accuracy. And sometimes molecules have triplet ground state, in which case in the ground state, HOMO and LUMO orbitals are populated by single electrons. Then there are even more transitions possible between different parts of the system. So we have to include these oscillators to the environment as well. And this idea of replacing transitions by oscillators, of course, inspired by random phase approximation, which is widely used in quantum chemistry, and in physics it is used even more, I think. Next, suppose we consider our system, which is 2 orbitals and 2 electrons. This system has 6 possible states. Electrons can populate both one energy level, a second energy level, and there are also 4 possible states with 1 electron populating 1 level, but with different spin orientations. This system, Hamiltonian, if we write it in this subspace of these 6 states, it will be 6 by 6 matrix naturally, but it has an interesting structure. It has a 4 by 4 block and 2 uncoupled states. This is not surprising because we have spin conservation. And that means we should have a triplet state with 3 states that generate energy. Those states correspond to eigenstates of total momentum of the molecule, or total spin, better say. That is why we do not actually need to solve 6 by 6 matrix, we only need to solve 4 by 4 matrix. And for 4 by 4 matrix, we need 2 qubits to encode it on a quantum computer. This is shown here. We have a sigma 1, sigma 2, x, y, z components, and this is just identical representation of this 4 by 4 block. And matrix elements of this matrix are just taken from original Hartree-Fock simulation. These are energies, which are these hopping matrix elements between energy levels, and also charging energies and exchange integral, all of them expressed in terms of Coulomb integrals. Now, what about the path? The path, as I said, is transitions between these orbitals. The frequency of every oscillator is just the energy difference between excited orbital M and W-quiet orbital alpha. So the length of this arrow is the frequency of the oscillator. But oscillators, unfortunately, interact with each other. If one looks at the Hamiltonian, one finds out that the interaction term between two such transitions should be represented like this, where A and A dagger, these are ladder operators of the oscillators, which introduce an coefficient in front is again this Coulomb integral, which I introduced before. We of course know it because we have run the Hartree-Fock simulation at the very beginning. So the Hamiltonian of the bus then consists of a set of interacting with each other oscillators. It's given by this line. This is not sometimes very convenient because in condensed matter, usually the oscillators in the environment do not interact with each other. To achieve this, we just need to diagonalize this Hamiltonian by introducing normal modes. And then it requires this diagonal form where this frequency is capital omega. These are actually excitation energy of the triplet states of the molecules. This is very important information. Basically, by diagonalizing this Hamiltonian, we already, sorry, I said triplets, these are actually singlets. We get the singlet excitations. Next, this is a full Hamiltonian, rather complicated expression, but what I want to show is just the general structure of it. We have 3 terms: system, environment, and interaction. System requires 2 qubits to encode it. Environment, it is a very long set of qubits which do not interact with each other. Here I replace oscillators by qubits because it is easier to simulate in quantum solver and in quantum computer, but the accuracy here is not suffering. It is the same as if it would be oscillators. And the reason for that is that the coupling constant G in the interaction terms are very small. And this plot, I just illustrate this. So if we have very small coupling between the environment oscillator and the system, then the, let's say, the population probability of the ground state is close to 1. The population probability of the first excited is G squared, and the second excited is G to the power 4, which is very small. We can just neglect it. And then we can, from every oscillator, we can cut out 2 lowest levels and use a single qubit to encode it. That's what I've done here. And then the interaction term contains these products of 3 Pauli operators. 1 comes from the environment, and 2 come from the system. So this is basically the general structure of the Hamiltonian, which can be easily encoded in a quantum solver presented by Hannah and solved. Now, unfortunately, as I said, easily, but of course, the number of qubits in the environment is so huge that one cannot do that. These are many thousands, actually, and all of them are important. So what one can do? It turns out that this coupling constant G are usually very small for most molecules. One can just use perturbation theory. If one does that, what comes out is a renormalized system Hamiltonian. So we should use this, evaluate this lump shift, so-called lump shift for the Hamiltonian, which is the average value of V in the dagger, where this is, let's say, deviation of interaction term from its average value, averaged over the environment. This integral can be easily evaluated in Markovian approximation. At the end, the system Hamiltonian retains the same form as before, but all the parameters are renormalized. For example, charge and energies become smaller, Coulomb interaction and exchanging, everything gets smaller. And the reason for that is just very easy. So one can think of every molecular orbital as a metallic grain. If you have single metallic grain, it has high charge and energy. If we couple more metallic grains to it, then there is additional capacitance added. And the overall charge and energy goes down. That is very simple. Now, if we need the lowest excitation energy, we just need to diagonalize this 4x4 matrix. And this is very easily done, and it is actually rather accurate, but not accurate enough. I have tried, for example, for 33 molecules, average error of such approach is 0.3 electron volt compared to very accurate quantum chemistry simulation. It's not bad, but chemists want more. They want higher accuracy, so-called chemical accuracy, which is about 6 times better than that. How one can achieve that? One can do the following thing. Even though we cannot solve all qubits exactly, we can solve some of them. So we should sort qubits and take those which are coupled to the system strongest. And we can take NQ of such qubits and then vary this number and see what happens. So, and those which we do not solve exactly, we still go put back into the lump shift. So the Hamiltonian of the system then again has this renormalized form where the sum in the renormalization runs from NQ plus 1 to N, only over weakly coupled qubits. And the interaction term only contains now NQ qubits. Now we can vary this NQ from 0, which then gives this static approximation, which I have introduced before, to 62, which is the upper limit for quantum solver at the moment, because quantum solver can only solve 64 qubits altogether, and 2 qubits we have in the system. So the Hamiltonian then formally has this huge size, which memory of no laptop memory is certainly insufficient for that. But as Hannah has explained, one can cut out the important part of the matrix and only diagonalize it. In this case, the important part is the limited number of excitation. So we allow in the environment only 4 spins to be excited. So most spins, let's say, point down, and only 4 of them point up. If we project this Hamiltonian to Z subspace, we can diagonalize. And this is actually accurate enough. This corresponds to, in quantum chemistry, to certain approximation, which is called SEPA, for those who know quantum chemistry. Then this is the final result. Basically, suppose we have this molecule, cyclopentadiene, then coupling strengths here. So we pick the strongest couple, the strongest spikes. There are actually very many oscillators for this molecule, and the basis set def2 TZVPD. The total number of oscillators is basically 4,000. Out of those, we take NQ, and the rest put into the lump shift. So this is the result for the first excitation energy, triplet, singlet splitting, basically. The accurate result calculated by this advanced quantum chemistry methods coupled clusters is shown by this blue dotted line. This orange line shows the static approximation, already rather accurate. As you can see, the difference is less than 0.1 electrovolt for this molecule. But if I vary NQ and include more and more qubits and solve them exactly, the result approaches this accurate value very, very closely. This is basically the whole point. And we achieve better than 0.043 electron volt error, which is chemical accuracy. Chemical accuracy is 1 kilocalorie per mole, which equals to that value. And the same I have repeated for 3 molecules altogether. Actually, we are now looking at even more molecules. And this is basically a summary of my talk. Thank you, and I give back to Nico if he wants to say something else. Yeah.
Thank you very much, Dima, for this very nice presentation of these really cool results. So hang on, let me maybe share the last thing. And just remind you that you can ask questions via the Q&A function of Zoom. And to give you some, there are no questions yet. So if you still want to think of some, I'll give you some time by giving a brief summary of things that we would very much like you to take home with you today. So first off, the singlet triplet splitting accessible with electron spectroscopy is actually an interesting topic. It can have technical applications, and calculating it in the usual way on a quantum computer is not feasible in the near term. But if one uses clever approximations and this RPA-inspired approach, it can be brought into a form that is much better suited to be mapped to quantum computers. Of course, that comes with certain approximations or certain assumptions. Mainly here that the bath, this bosonic bath that everything is mapped to, is not highly excited, and one can then further on map it to the qubits on a quantum computer. And that means we can also use these approximations or these assumptions to make the task easier for a classical computer. So we can actually test it out for system sizes that are not trivial, here up to over 60 qubits. But that also means we are still running at some point into a limitation of how big we can go with a classic computer. And of course, eventually we want to run this on a quantum computer to get even better results. All right. Thank you very much for attending today. And I hope you have a nice rest of the day, evening, in whichever time zone you are.
Okay.
Bye.
Bye. Thank you.